please. Can you see my full screen, Zach?
Yes, doctor.
Okay. So this is the simplest case yield mode of failure. Okay, if you reach, in this case, which is, there is only one member of the stress tensor, sigma x. If that value reaches sigma y, yielding, you have failed. That's it. Now, what happens if you have more than one element of the stress tensor? Okay, for example, this is the next case. Okay, you have plane stress, and that's our case because usually we have sigma x, sigma y, and we have also tau xy. Okay, and in this figure, this is a classical figure. You see that I have sigma 1 and sigma 2 divided by this is the yield point. Okay, and we see that there is a value of 1 here and a value of 1 there. Sigma 1 and sigma 2, remember, are the stresses, the principal stresses using Mohr circle. That's something that you studied in solid mechanics. Okay, now, here, I'm showing you 3 theories. One theory is the maximum normal stress theory, is this one here. And you see that for this type of material, in this case, gray cast iron, that's brittle materials, okay? You see that you can reach this value here, this is little triangle, and you still have no failure. So that's telling us that for this case, for this type of material, brittle material, this theory of failure, maximum normal stress theory, it's adequate. Okay. Now, if we see this point here, what means failure, and these are for these materials, and these are ductile materials. Okay. You see that, for example, you have steel. You have aluminum, another steel, different steels. So these are more ductile materials. And you see that these points means that you can reach only here, not here, as the brittle. That means that for this type of materials, you see all of these cases, we have to apply a different criterion. And there are 2 here. This is the maximum shear stress theory. So you define this figure, this, and that. And if you are inside, you are safe. If you're outside, like all of these, that means that you can expect failure. And finally, there is a octahedral shear stress theory, which is the most common. Okay. And in this case, I'm sorry. In this case, you have this figure here. See that all of these points are just on the border. That means that this is quite applicable theory to judge the maximum allowable stress in the case of ductile materials. Okay, now, how is this sigma 1 and sigma 2 related in the case of the octahedral shear stress theory? Well, in that case, what you have to do is you have to calculate the von Mises stress. This is not really a stress. This is just another parameter which has units of stress, okay? And this is the way they are defined. Okay, you have sigma 1 and sigma 2, and these are the principal stresses in the case of the Mohr circle, right? Or remember that sigma 1 and sigma 2 could be expressed as sigma in terms of sigma x, sigma y, and tau xy, right? And in that case, this is the way this von Mises stress is expressed, okay? Now, if you are inside the circle, that means that this value here is below the yield point. So if this is below the yield point, you are inside and you are safe. And that's the criterion. Okay, so the equivalent or von Mises stress is defined in this way. And if this resulting value is less than the yield point of the material, you are inside and you are safe. You cannot expect failure of that material. Okay? Any question, people, so far? Okay? So let me go back. Example here, okay? In this example, I would have a sigma x, which is negative, a sigma x, which is also negative. So these two will add, and I have y. Sigma y could be positive or negative, okay? Because on the thickness, I have both cases, on the top or on the bottom, okay? I'm going to do an example, don't worry, in a few seconds, well, not in a few minutes. So you have sigma x, sigma y, and here you have this term, which is the combination. So we have to be careful, okay? Because if you use the correct stress, you could have an addition to that or a subtraction. Of course, we are conservative, so we have to consider the worst situation, right? So my question for you would be, if sigma x and sigma y have the same sign or a different sign, will represent the maximum equivalent von Mises stress. What do you say, Mr. Tenemea? Sigma x and sigma y should have different sign or the same sign in order to have the maximum equivalent stress. Mr. Tenemea?
Doctor, in this case is if change the sign is the sign, but is not the effect.
No, if you change the sign, for example, if sigma x has different sign than sigma y, the result of this is going to be negative. And with this negative sign, the result is going to give you positive. And these two are positive because they are squared. So what I'm saying is that you need to consider the point where sigma x and sigma y have different sign. In that case, this term will add to these two, and you have a larger stress. So that's very important because in some cases that will occur on the top or on the bottom of the plating. Okay, so all of that should be in your head. Okay, just to remind you, just a little reminder. We're mentioning, we're talking about the plane stress situation, right? If this is sigma x and this is tau x, something like this is a more circle. So you have, for example, this point here is going to be sigma x and tau xy. This is for 0 degrees. And you plot it like this. This is sigma y. And this is tau by x. So this is valid for 90 degrees. Okay, so you have this x, you change 90 degrees and you go to sigma y. So that's what you have here. Okay, so that's your Mohr circle. And in here, this is what we call sigma 1, and this is what we call sigma 2. Okay, so if I give you sigma x, sigma y, and tau xy, you could develop this this circle, and you can calculate sigma 1 and sigma 2, or you can directly employ this equation with sigma x, sigma y, and tau xy, and you can apply this directly and calculate the equivalent von Mises stress. Both cases are equivalent. Okay, so sigma 1 and sigma 2 are the extreme cases, the principal stresses, they have sign. So this term here is very important. You could have sigma x, sigma y, and tau xy and apply this formulation. And the thing is that you have to compare that with the G point. If you are below 235 megapascals, you are fine. If you are close to 235, you start worrying. If you are above 235, you probably need to increase the thickness. People, is there any question about this? Any questions?
Doctor.
Yeah.
Good morning. I had a question. And in the value on the tau 1, is necessary obtain the tau in primary
Yeah.
behavior, and
Yeah.
plus the secondary tau x.
Yeah, but usually that's what we were discussing here, right? In this case, the secondary or the tertiary, basically in this case or in that case, okay, the shear stresses are very small. We could calculate the shear stresses here and here. They're going to be very small. Why? Because in general, the height, okay, of the web is going to be very small. So in general, I don't expect in this or that case. This case, remember, chapter 4, we started saying that tau in the vertical direction is null. So we have only stresses in this direction. And these are in general very small. In this case, no. In this case, there are some importance. Remember that on the side, there is large values of the shear stress. Let me remind. For example, let's suppose that we have a barge like this. Okay, let me change color to draw. And we said that if we had to calculate the shear stress, that would be something like about this variation. Okay, and then on top, this value will be close to this one, and it will be a reduction up to here. Similarly in here. Something like that. So in this area, okay, we are quite away from the neutral axis. So the normal stress will be very high. And also, you see that in this area, the shear stress is important. Okay? See that this value, it's important. It's not the maximum occurs here, but it's not that small. In the central part of the section of the deck, that's something that Ms. Santos was asking me. In this area, how much is the shear stress, Mr. Carranza?
0.
0. In this area, the shear stress is important, but here is 0. So that's why in this area, we usually include a little bit more of thickness than in this area. Okay, in both, the normal stress is very high, but on the side, not only the normal stress is very high, but also the shear stress is important. Okay, did I answer your concern, Mr. Carranza?
Yes, doctor, thank you.
Okay, no problem, no problem. Okay, people, so this is what we're going to apply for the next example. Okay, we're going to calculate sigma 1, sigma 2, sigma 3, and then we're going to do a combination in a certain point. And we're going to check with a real ship that this is really satisfied. Okay, so let's do it. Okay, so this is the ship that we're going to be analyzing. I didn't want to put it here, but the name of this ship is the Richwing. I had to analyze the stability of this ship many years ago. it was developed for Ajax Classification Society. So the inclining expelling was strict, and all of these calculations has to be very precise. Anyway, so it was a nice example for me. Okay, so this is the ship that we're going to be analyzing. As you can see, it has double bottom, not double side, not double hull. You see that here on the side, there is no empty space. Here, there is some empty space. So this double bottom, not double side, okay? But we still can analyze it. Longitudinal framing. Okay, so we can expect the longitudinal to be closely spaced. And in the transfer direction, there's going to be a larger spacing, okay? These are the main dimensions. 72 meter, this is the length for scantling. Remember that length could be, there are several options. Overall, between perpendiculars could be waterline and so on. And there is, to apply the regulations from the Classification Society, you have to calculate a specific value for L, okay? Then you have to consider that between perpendiculars, and you have to include a little bit, and then you have to make a comparison, and finally establish what is the length to apply the regulations, okay? This is the depth, and this is the draft when it's loaded. So you can see that, what's the difference between these two? What's the name of the difference between these two? Ms. Valdez, if I calculate this minus that, what's the name of that parameter of the hull?
Freeboard.
Yes, that's a freeboard. And in this case, how much is that, Ms. Valdez? In this case, how much is this? How many centimeters?
0.65.
Yeah. Can you show me with your arms?
One moment. I can turn on my camera.
Okay, that's fine. What I'm trying to tell you here is that, okay, this is a 75-meter long ship, okay? Is the soccer field, probably a man knows that. Mr. Dominguez, how long is the soccer field? Do you know? You play soccer, Mr. Dominguez?
Yeah, but I don't remember the length.
The length? Anybody knows the length? Engineer Isaac, probably you know. What's the length of the soccer field, Engineer Isaac?
I don't remember that.
Come on! It's about 100 meters. It's about 100 meters. Okay? Also, a block, okay, in your neighborhood, a block, and a standard block has 100 meters long. Okay? So this is 75. So it's a little about 3/4 of that. So what I'm trying to tell you is pay attention to these things. Okay, so if you go and try to analyze, okay, so it's a 75. Okay, so you see that length over beam, L over B, it's about what? 6 times, right? So these numbers have to make some sense to you, okay? So it's about between 6.5 probably about that, okay? Now B over D is about 2 to 1. That's typical. So it's just 2 point something, but it's close to 2, okay? People, start making some sense. And finally, you see that in this case, 70-meter long ship, and the freeboard, as Ms. Valdez said, it's 65 centimeters. So it's about this. It's not much. Okay, so start making some sense. For example, if I ask you, let's analyze a 100-meter long ship. What would be what would we expect the beam to be for that ship? Ms. Arechua, Engineer Arechua. let's consider a 100-meter long tanker. More or less, what would be the value that you would expect for the beam?
For the beam, 15.
Yeah, 16. Yeah, 6 to 1. And how much it would be the depth of that?
The depth of 100 of length.
So if you're saying that you got 16 for the beam, how much would you expect for the depth?
For the depth, 9.
Maybe half of that. So it's going to be about 8.
Oh, 8. Well, more or less.
Okay, more or less. But that's what I want from you people. This is not just mathematics. This is engineering. And finally, Mr. Villalba, what would you expect for the freeboard for a 100-meter long tanker? That's a good one.
Freeboard.
It's a good one.
Increase.
More or less from 70 to 100, how much have you increased from 70 to 100? It's about what, 1.25, more or less, right? 35, no, a bit more, 1.4, let's say 1.4. Yeah, 1.4. So what I would expect is an increment of 40% from the actual freeboard. Right now, the freeboard was, Ms. Valdez, what was the freeboard?
.65.
0.65. So half of that is 0.32. So it's an increment of 0.25. So probably about 0.9 meters. People, that's application, the practical application of these things. It's not just to show you something. Now, let's go on. Here I have the light ship. Remember that when you do inclining experiment, one of the things that you try to determine is the condition at light ship. Okay, so you do calculations and finally you consider that the ship is just steel and machinery. That's all. There's no nothing, no loading, no cargo, no fresh water, no fuel, no people. Steel and machinery. That's all. That's the light condition. In this case, you see that there is a 641. Okay, this is the draft 132, and this is a trim in that condition. Question: how much is going to be the draft in the forward end? Ms. Santos, what's going to be the draft at the forward end?
The double.
I don't know. You just tell me. I need a number. Engineer Santos. Don't tell me a lot or just a little bit. No, I need a number.
2 meters.
The draft at the forward end. Mr. Chinchin, in the light condition.
7 points.
What? The draft at the forward end.
Okay, is the rest about the draft and the tip, the trim.
How much is that? Come on.
2.06.
If I divide this by 2, how much did you get?
1.32.
So that's 132 is going to be reduced on the forward end and will be added at the aft end. So how much it will give you at the forward end? How much will give you?
2.64. No.
No, that will give you 0. So you have the ship. Mr. Rich went up. Was like this. Like this. So about here, this is 132. And then you have here, so the distance from here to here, that's a trim, that's 264. So the forward end, in the light condition, the condition that we tested was basically, you see the forefoot was just touching the water. So the draft at the forward end was 0, basically. That's typical in the loading condition of a tanker. Okay, this is just to start practicing what you have learned in previous classes, okay? So all of this, you are responsible for all of this, okay? So you are responsible for all of this. I'm not going to give you the details. See, all of this information probably it's going to be combining. I'm not going to give you this directly to apply. No, I'm going to give you so that extra information. So you have to deduce what you need. Okay. Right now, I see that there is only 12 students in the class. Isaac, is that correct?
10. 10 is 2.
Okay, so please, this is the number that I need because I want to see how many we stop. Thank you very much. Okay, so let's go on. Now, this on the left, it's a plan. This is taken, remember, from the beginning of this chapter. People, you are responsible. This figure, and there was another figure at the beginning of this chapter in which we explain the framing system, okay? In that figure, you have all of this terminology, okay? So there was an A and a B. The A was the same ship, but with transversely framed double bottom. And this is for the longitudinal framed double bottom. You are responsible. This is being recorded. You are responsible for the terminology of all of these terms, okay? All of these elements, structural elements, okay? I don't know how I'm going to evaluate you, but I am going to do it. So you have to review all of this terminology, okay, people? You are responsible for that, okay? So all what I'm trying to show you here is that this is from a book, and this is the real Richmond instructor, and you will see that it's basically the same. So it's like they build it according to this ship, okay? So this is the longitudinals. You have the longitudinals here, okay? And you have you see that there is a sign here, and this is what we call the intercostal side girder. Okay. So you calculate the distance from here to here, and that's about 2.5. Okay, so the beam was 11.2. So from here to here, how much is going to be from here to here, Ms. Valdez? From here to here, how much is going to be that? Here to here, Ms. Valdez.
Yes, doctor.
Come on, you don't need a calculator for that.
No.
Come on.
Only estimate a value.
No, if the beam is 11.2, how
Okay.
much is from here to here? Give me a value. Yes, exactly. You can divide 11.2 divided by 2. That's how much? Come on.
5.6.
Yes, 5.6. So from here to here, 5.6. Now from here to here is about 2.5. So that's the maximum distance. Remember, that you can apply, you can have a side girder, right? If you have more than that, probably they will not accept this the structure because it's just too much. Okay, now in here, you use 5.2, you have 1, 2, 3. So the spacing between longitudinal is going to be 2.5 divided by 4. Okay, all of that has to start making some sense to you. Okay, now here I have some information, the spacing between floors. Okay, the floors are the primary transversals. Okay, so if you see from the side of the ship, okay, you have transverse bulkheads, okay, and they are separated, I think it's 10.8. So you have every 2.7, you have a strong transverse frame, and that's what we call a floor. Okay, 2.7. Between primary longitudinals, so it's from here to here. So this is the side girder, 2.5. Longitudinal stiffener, so is if from here to here you got 2.5, you got 3 of these, so the spacing between is 0.625. Here is just 0.63 because I needed more space. Okay. So this is a double bottom, and the height of the double bottom is 0.85. Okay, so start thinking about 0.85 is about this. Okay. If you were the engineer who built this thing, you have to go inside 0.85 and check that the welding is really well done. Okay. You still want to be a naval engineer?
Yes.
Okay. Now, so let's go on and do the analysis. Okay. So this is extra information. So that's the spacing between bulkheads. The double bottom height is 0.85. Now, this is, we consider that this is built with common steel. So this value have to be considered. Okay. In the past, we used other units. We are just keeping international system units, so 235 megapascals. Okay, so let's go on. So first, let's calculate the required salt section modulus. Okay, so here, remember the S here is for the still water. So you could put all your weights, calculate the mean draft, calculate the trend, and then you could calculate the distribution of bending moment. That you can do that, but the classification society, they give you this expression to approximate that. And since this is 0, that means it's around the midship area. Remember, it was like a trapezoid, increase linearly, constant, and then decreases back to 0 in the forward end. So this is the central value, and this is the result. Later on, you can do the calculations. Then we need to do the estimate the loading or the bending moment in waves. For this, we have, do you remember how do you say quebranto in English? Miss Acuña, how do you say quebranto in English? Miss Acuña?
Hogging.
Hogging. Mr. Gomez, how do you say arrufo in English? Mr. Gomez? Mr. Gomez, hello. Mr. Gomez. Mr. Villalba, how do you say arrufo in English?
Sagging.
Sagging, yes. So this is for hogging, this is for sagging. Remember, sign is very important, okay? So this value here is the minimum between these two. And this is very close, okay, to L over 20, which was a typical value for the effective height of the we have. Okay, this is usually positive, this is usually negative. Okay, Remember, a rufo, you have two crests on the side. So the ship smiles. But according to the Classification Society rules, this sign is negative. So there. Now, this is what we're doing. Basically, this is the stress that he's thinking. This is allowable stress. This is the bending moment, still water, plus waves, and the result is this. So this is the required section modulus for the whole section. Okay, so you have this plus that because they have the same sign, divided by 175, and this is the result. But remember that we just discussed that there are some limit states. One is the accidental. And my understanding is that this is the accidental limit state. The rule says that you have to have this value of minimum section modulus for the whole, but this value be lower than this. And my impression is that this requirement is like the other limit state. It's like the accidental limit state. So this is like the common situation, floating, navigating in waves, and this is like an extreme situation. For example, when you ground, or you go into on the dry dock, and you sit on blocks, and they exert very high concentrated loads. Okay, so obviously this is a larger value, so the requirement is going to be that this is the minimum value that we have to satisfy, not this one here. Okay, so this is the requirement. Now, to do this check, what we have to do is to select the thickness. To select the thickness, we have to consider basically tertiary behavior. Okay, and for doing that, we need to calculate the design pressure. Now here, this is the section, and different parts of the section. For each one of these plating, we have a different loading, different pressure. So this is a summary of that. This is specifically applying the regulations for ships with length less than 100 meters. Okay, so we have the outside bottom, this is this. Inside bottom, this is double bottom. This is for the side, for the deck, and this is for longitudinal elements, very strong element. Okay, this is floors and longitudinal side girders. Okay, so for each one have a certain value of the pressure. Okay, check all of these. We can comment on that later on. Okay, and this is the result. Now, you see here that the problem is that when you have liquid here, okay, the liquid is possible that you do not stop the pump at the correct time. So it is possible that you fill all of this, including this pipe, with water. That means that the height, okay, to calculate the pressure on the double bottom is not up to here, but up to here. Okay, that's why we have a higher value, 4.9, and this value is larger than this one here. Because by mistake, by accident, you can expect to have all of these, including the tube, filled with water. So that increases the pressure acting on the double bottom. What happens on the bottom? What happens on the bottom is that you have downward and upward, and they tend to cancel. So it's possible that this is empty. So you have pressure acting upward, and that's this value here. Okay? And you see that on the deck, you have the lower values. Since this is a tanker, you don't expect in general to have a large value of loading on the deck. Okay, but still from time to time, you can put, for example, a welding machine or something like that. So you have, in general, this value tends to cover that situation. Okay, now, we have value of pressure, we can proceed and calculate the thicknesses, okay? And for this, what I tried was to compare, for example, bottom, the side, deck, and inner bottom, okay? These are the values that we had before, okay? Here, this is the aspect ratio. So basically, this is 0.625 divided by 2.7. Okay. The value of the coefficient from Timoshenko. Okay. This is the ratio of 235, and this is the stress, working stress according to the classification society. Okay, so you take 235 times 0.51, and that's the result. And this is stress, allowable stress from DNV. Okay, so with beta, pressure, and aspect ratio, you calculate the moment at the pit center. And with that, you can divide, you can apply this formulation in order to have the thickness, the required thickness. Then we apply this formulation from DNV. And you see that these two values are very close. Basically, this is what DNV is using. Basically, they are considering plate bending. But remember that I also said that the thickness has to be no less than this. And this again is, for me, is the limit state for accidents, right? From time to time, you have a concentrated force on the deck plate, and you didn't consider that here. So you have to consider here. And you see that this is larger than that, larger than that, larger than that, larger than that. Okay? Now, with these values, we could go on and try to determine the sectional inertia of the ship. Okay, we have calculated the minimum value, which is this 588,000 cubic centimeters. Okay, in this, we have selected the thicknesses. Okay, now we put this section and we can calculate the sectional inertia. Okay, and this is not adequate, we have to increase. Okay, for example, let's check. The bottom is going to be 7.88, and this includes the corrosion allowance. So everything is in here. So I'm sorry, this does not include the corrosion allowance. So we have to increase a little bit that. Okay, so I go from 7.88 in the bottom. Let's see in the section. This is the real. These are the real thicknesses taken from the plan. Okay, so in the bottom, you have 9 millimeters, and before you have about 8. So this increment means that you have increased because of the corrosion allowance. Okay, so you have deck plating, bottom plating, double bottom, side. In this case, you have 1 and 2 sides, and the longitudinal bulkheads. In this case, this is just a first approximation, and we are not including the longitudinals. The longitudinals will increase a little bit, but not much. Okay, so this is very common calculation for us. This is something that we have to have in our mind, how to set up this table. Then here, this is the result. The required value is 588,000. Here is more precisely 588.8. And this is the result, 600,000, including this formulation. So this is just a little bit above that. I did this, okay, since I have this in an Excel table. I changed this thickness. instead of in the deck, instead of 0.8 millimeters, I put it 7.5. And that prevents this from being above this value. So we're just increasing until finally we satisfy this requirement. Now, we know that if we include the longitudinals, okay, in general, we can expect an increment, but don't expect too much. Okay, don't expect too much. What I'm trying to say is that in this case, okay, the plating is the main element to support primary stresses. Okay. Now, let's go to the floors. Now, you see that this is a longitudinal side girder, right? And this is what we call a floor. So this is a transverse element, very hard, very strong, which supports the longitudinal, the stiffness. Okay, now, of course, if you have a very high element, the bending will be not of a problem. But this is a plate which is dividing different tanks. So what we can consider is that this plate, it will be supporting pressure, lateral pressure. Okay, so it's like a plate on bending. So we have to calculate the pressure, and that's why here we calculated the pressure on this element here. So that's why we consider this height 5.33. So this is the pressure that will be acting on the floor on the side girder. Okay. So this is a plate. So we need the spacing. I'm sorry, the aspect ratio of the plate. So it's going to be, this is the spacing here to here. And this is longitudinal, I'm sorry, this is the height. Okay, so we're considering this element here, this plate here. That's that. Now, I'm sorry, this is the longitudinal. Okay, so in this case, it's going to be the spacing in this direction, which is 2.7. And this is the height, which is 0.85. So that's that. So this is 2.5, so 0.85, 0.85. This is 2.7 divided by 0.85. And now we do a similar analysis than before. Okay, so this is the calculation of the thickness according to Timoshenko. This is according to DNV. And again, they apply this formulation. This is for the common limit state. And this is for the accidental limit state. Okay, so in this case, you see that this is the value that we have to consider. This one here, because it's larger. Longitudinals, okay, so this is a side view of the structure. Okay, so this is X, this is Z, and this is the double bottom, this is 0.85. This is the height of the double bottom. So what we can do is we consider this is a floor. Okay, this is a triangle. So this is a beam which could be considered as clamped on both ends. Now, in some of these, there is a connection between this is the longitudinal of the double bottom and this is the longitudinal of the bottom. As an extreme case, we could consider that this support does not exist. So this is the length, unsupported length, which is 2.7. Okay. So that's what we are going to consider. Okay, so since we are considering this as a beam, we need to calculate the force per unit length. So that's the pressure times the spacing, 2.7, the distance from here to here. This is the working stress. So this is the required section modulus, 163 for this guy here. Okay, but now we could apply the formulation from DNV. This is the formulation from DNV. Okay, this is the rule. And this is the result. So basically, this formulation tells us that they are considering from here to here, it's an unsupported in the bottom. So you see the relationship between what they are doing with what we obtained applying chapter 1. Of course, once you see these, immediately you start thinking, okay, this is bending. Calculate here the Z. You need to include part of the plating to which this web is welded. That's the effective breadth. We will talk about that in the next session. Now, the longitudinal in the ship, okay? In the ship, this is what we have, okay? This is according to the rule. It says that if you have a stiffener, the plating is 100% effective. So this is the spacing between longitudinal. So that's all of this from here until here, according to the rule. These are the thickness. These are the dimension 15 by 9 of each one of these elements. And this is the result. Well, we have to be careful here, okay? Because with this, I'm going to stop because this is the plating, okay? This is the stiff, like this. The neutral axis is about here. And you see that this, the height is 15. So from here to here, this is 15 centimeters. And the position of the neutral axis is 2.86. Okay, so that's okay, so that means that the stress on the flange is much larger than the stress on the plate. Okay, and here we calculate the stress at, I'm sorry, the bending, the suction modulus on the flange is 161. And the required, applying the formulation, is 162. So basically, we're just understanding what the Japanese people did. Any question, people, so far? Any question, people, so far? Questions? Okay, please, for this coming Thursday, we are going to complete this example. And I'm going to describe the transfer situation. And from that point, we're just going to comment on the classification rules, okay? There are some information which is quite useful. And the idea is that you start recognizing the relationship between what they do or the expression that they include in the classification rules with our formulations from mechanical structural mechanics and so on. But that's the idea. If you have questions about the homework, please send me an email. I'll try to help you as much as I can, okay? If possible, tonight I will be available to you to answer questions about the assignment, okay? At 8 p.m. As usual, even though today is Tuesday. Now, tomorrow, remember, we have the student technical sessions. It's in person. I invite you to come. It's a good idea for you to see, okay, how these things are done. And the idea is that after you complete the program, you have several opportunities to participate in the technical student sessions. The idea is that you practice doing presentations and presentations in English. So if you can do it, please come. And that's going to be a nice opportunity for you to see what others are doing and learn and learn from, because you can ask questions, learn from other experiences. Okay, so if you can, please come tomorrow. Okay. Is there any other question, people? Then I'll see you. Hopefully, I'll see you tomorrow. Otherwise, I'll see you Thursday. No questions? Okay, you can stop the recording, Isaac.